Okay, hello and welcome to Textile Build. Thanks so much for joining us today for our first ever Textile Build training session. Hopefully everybody can hear me clearly. If not, please leave a message in either our Slack channel or our Ask a Question channel with the link up at the top there. So for those of you joining us live, there are a couple of ways that you can ask questions and interact with the Textile Build team during the session. You can use the link at the top of the screen, which you should be able to see there, with the hash G7JHNA. So you can post questions there, and the speaker, should be able to hear them or see them right away. You can also join our Slack channel, and you can click the links to those two icons on the slide there if you have the slides. And you can ask questions directly in the Slack channel as well, and our team is there to answer sort of clarification questions or technical issues. So this is the basic structure that we're going to be following here today. We might go a little longer than anticipated today just because we've got quite a few items to cover and we've got a little bit of administrative things to go through to introduce the course. But first things first, I'm going to do a really brief introduction to Textile and our build series, followed by a couple of quick admin things, and then we'll just jump right into today's session. So let's do that. So Textile, the company, is a relatively small startup with a fully remote or decentralized team. We have folks in the Bay Area, Mexico City. I'm coming from Victoria, BC, Canada, and we even have an extended team that we work with in Europe. Our main focus is on privacy, transparency, and decentralization, obviously, with a core focus on the user experience. So our big kind of push here is that decentralized systems have a lot to offer the consumer web, and we want to bring those benefits to users with minimal overhead, minimal effort. Our first product, called Textile Photos, is a digital wallet for your photos that runs on IPFS, and a couple of big ideas that we have about the future of privacy and what that should look like. We have a big focus on privacy and security, so a lot of our development time is focused there, and so we will touch on some of those topics throughout this course. So feel free to check us out on those links if you feel like. We're a fully open source team, so you can take a look under the hood and see what we're up to there. All right. So the Textile Build series that we're working on today is really a bit of an onion course. And it's an initiative that spun out of some of the tutorials and community engagement materials that we've been developing over the last few months. And one thing we noticed is the decentralized web community is super excited and is moving really fast. But you end up doing a lot of building and learning on the fly. And so this makes it really hard to stay on top of the latest and greatest developments. So we started creating these tutorials for ourselves. Then we started sharing them with the wider community. And then given the background of some of our team members from academia, it kind of made sense to turn these into teaching materials. It's also a way that we can give back to the IPFS community and sort of try to bring people over to the decentralized web. So as I said, this is what I like to call an onion course. So we'll start really broad and slow, and things will get incrementally more detailed and slightly more difficult as we move through the course. So if you find the content a bit slow to start, that's okay. We just want to make sure that everybody's on the same page starting out. So we'll sort of do a wide range of topics, and each week we'll get into more depth and less breadth about different decentralized web technologies. We may jump around a little bit if people are asking for specific additional information, but that's the general concept there. Okay, so hopefully you're already aware of the topics for this course. Otherwise, it would be weird that you signed up. But just in case, here's a quick review of what we're going to go through. So we'll get through bits of both of these first two topics mostly today, and then we'll move on to some actual development work at the next session and throughout the session. So there won't be a lot of actual JavaScript or dApp development today. This is more of a introductory session today. Speaking of which, here's the session or the schedule that we'll mostly be keeping to. as I said, I'm not going to promise that we'll finish exactly 1 hour each session, but I'll do my best to make sure that we do. And there will be a little bit of homework that you need to have done, or I'd like you to have done between sessions, but none of it's particularly difficult, and it's really just designed to fill in a few gaps and things along the way. Okay, so I'm going to leave this on the slides here. You can take a quick look. Basically, I'm going to make a couple of assumptions about you and your level of development experience. So I'm going to assume you have done some software development before, that you're fluent-ish with the command line, that you're able to perform certain tasks like running scripts, git cloning repos, and changing directories, etc., and that you're somewhat familiar with JavaScript. In most cases, we will actually be just copying and pasting code for the most part, but I'll assume you have some idea of what you are copying and pasting. And we do have sessions. This lesson is live, but we do also run office hours each day that we run a live session at 6 p.m. PST. So we'll do another live office hour later today. Okay, so the man behind the voice here is me. I'm Carson Farmer. I am lead data scientist at Textile and assistant professor at the University of Colorado Boulder. I've been teaching things like this now for quite a while. This is a new course for me, so I'm pretty excited to get started. So in fact, let's just do that. So coming at you live from Victoria, BC, Canada, here is Textile Build Session 1. Okay, here we go, Lesson 1. Just have a quick look through that. We're going to really blast through these first couple of topics and spend a little bit of time on the command line to get you familiar and build up an intuition for IPFS and some of the concepts that come with the decentralized web. Okay, so let's start off here. And actually, before I dive in, I'm just going to take a quick look to see if we've got any initial questions coming up in the channel. It looks like we're okay. So feel free to just reach out if you have any questions along the way. That's what we're here for. Okay. Okay, so when you visit a website, say in a browser like this, and you access an image or a spreadsheet or a data set or even a tweet on the internet today, chances are you're accessing that content via some kind of a link or a URL that starts with HTTP or HTTPS. This link identifies the content that you're after by its location. So it points to a particular location on the web, served from a particular server using a particular port at a particular location on the planet. And then your client, your web browser requests some information, and the server will hopefully return it back to you. So if you visited textile.io in Firefox, and why wouldn't you, you would hopefully see a nice HTML page that looks a bit like this one. And there are a ton of things happening under the hood involving protocols and system interactions that are at work to bring that page to you. And it's a pretty impressive system. It's pretty impressive that the whole thing works at all, given that you could be sitting in your living room somewhere and accessing data or a web page sitting on some server across the planet. Now, I'm not going to go through how today's web infrastructure works and how HTTP protocols work. Plus, there are a ton of other videos out there to help you with that subject. And in fact, I'm going to be posting in these slides YouTube videos along the way, which we're not going to watch together. But I recommend that you go back and look through these slides and watch those videos, because generally I'll put them in there if they're sort of a light covering of a particular topic. So this one is actually quite engaging and surprisingly informative. And the first bit talks a little bit about what that HTTP infrastructure looks like. Okay, so as amazing as this modern infrastructure is, there are quite a few issues that have been bubbling below the surface for a while now. So for instance, what we have now is relatively far from the decentralized system of servers and clients that Sir Tim Berners-Lee had originally imagined when he sort of proposed this idea of a web, of an interconnected web. And what we have now is that there are relatively few large physical servers operated by relatively few large corporations like Google, Facebook, and Amazon that we've sort of given responsibility for hosting essential elements of what we consider the modern internet today. So what we really have is a fairly centralized web, a fairly centralized internet. And that's not necessarily an issue unto itself. Centralization can lead to all sorts of efficiencies. But when we're talking about this global information system that is the internet and that is the web, a centralized web can start to become a fairly vulnerable web. And we've already started to see some of these problems inherent in this type of system crop up. The biggest being the sort of disproportionate amount of trust that we end up having to put into these large corporations that are serving up web content for us. Right? And if you really start to think about the structure of our modern web and what it's become, you really start to see how fragile this whole system can be. And you can just take the example of some recent data breaches or privacy scandals to see that we're putting a lot of trust into a fairly small set of players. But there are other issues at stake here as well. So the whole system of a client-server system, the way we have it, means that if a server goes down or disappears, the link associated with that particular server will lead to nowhere. So this is what we call link rot. Servers can be hacked, which means we've got this sort of single point of failure for a particular service that we may not be very happy with. Companies and governments can censor access when we've got a single point of control like that. Personal data privacy often becomes a product, and this is a big focus of Textile, is sort of flipping that idea on its back. And then there's a big idea of trust. And again, there are lots and lots of videos and tutorials and blog posts about some of these issues with a centralized web. And I think I'm probably preaching to the choir here, because if you're taking this session, you probably already have an idea of why you want to start thinking about the decentralized web. So I won't dwell on these issues here. Instead, I'm going to focus on what the decentralized web should be. All right. Here's just a nice quote, right? So we're going to focus on decentralized web. And this focus is not just something I invented hoping that people would show up to a session that I created. It's actually something that we're starting to see renewed interest in. And we're seeing this interest in a vision of a decentralized web quite a bit lately in the news and on blogs and in a lot of probably company meetings and things like that. And you can just look as far as the Decentralized Web Summit that's happening this week, where the sort of best and brightest are gathering to plan the future of Web 3. Even Sir Tim Berners-Lee is there, and of course, half of the Textile team is there this week as well. And so some of the reasons for this renewed interest in decentralizing and decentralized technologies is obviously some of the issues we mentioned earlier, but it's also a growing need to archive and plan for a more lasting web. It's addressing issues of privacy and personal data, data access, security, some of the new issues that have come along with GDPR. A lot of these things have brought a lot of what the decentralized web is based on to light. And then on top of this, you can throw in blockchain, which is a recipe for probably a good startup anyway. Just think of something and throw on blockchain. And you've got a recipe for people paying attention to these types of things. So obviously, blockchain is everywhere. It's a great example of a decentralized system. It's a fun decentralized system to watch. And it's a peer-to-peer system. And we're going to talk about all of these types of concepts in a second here. So our first aside about blockchain here is it's a system to facilitate recording transactions. In practice, these transactions are often financial in the case of, say, Bitcoin, but they need not be, without the need for a centralized broker or any system to manage those transactions. So the idea is trust no one in particular, trust the system. It was initially introduced as the public immutable transaction ledger for the Bitcoin cryptocurrency, but it's found application in just about everywhere now. Probably you've heard of Bitcoin, Ethereum, a bunch of different altcoins, et cetera, et cetera. You really can't miss this stuff if you're following the news at all. In the end, you can basically think of a blockchain as an append-only database that is distributed across a network of nodes or peers that all collectively store the entire transaction history of that network. Okay, and there are a lot of different chains out there. Some more popular or well-known than others. Examples are, as I mentioned, the Bitcoin blockchain, where all of the transactions that are stored as blocks in this chain of transactions are financial. So, X party sent Y party in Bitcoins. Then the Ethereum blockchain is a sort of a different idea where you can have lots of different transaction types through the use of apps or programs containing rules for processing those transactions. And in the Ethereum world, these are called smart contracts. But either way, what we have is a system for storing transactions. Okay. A peer-to-peer system, which I mentioned a second ago, is a related piece of technology, and it's another key piece of the decentralized web puzzle. It's actually been around since the 90s and even ideas before the 90s. But basically, a peer-to-peer or P2P networks are networks designed to partition up tasks between the nodes on that network, or the peers, if you want to call them that, who are all equally privileged, so they can do the same things, and equally powerful, so they can accomplish the same work. And there are variants on top of this, but this is the general idea. So where have you seen this before? Probably, if you remember something like Napster, or you download movies legally, of course, and shows via BitTorrent, or you browse the web using a Tor browser. All these systems use P2P technologies in one way or another. And blockchain is also a P2P system. So the really cool thing here is that blockchain and its associated cryptocurrencies, which are all the rage these days, they've really placed a big and renewed focus on these trustless systems with cryptography and game theoretic incentive mechanisms right at the core of these. And what this has done is propelled P2P systems forwards in terms of usability, application areas, scalability, and generally just, people's awareness. So I think a lot of people love to hate on cryptocurrencies and just sort of hype that's around them, but they have done a lot for propelling forward some ideas about decentralized systems. So the vision of this sort of decentralized web is something like a peer-to-peer network built around P2P protocols where users own their data, data is portable, computing and storage resources are provided by end users within distributed networks, apps run locally on end user devices and platforms are decentralized and autonomous, and everybody is happy. And you'd be hard-pressed to find a really clear, agreed-upon definition. Maybe we'll come up with one this week at the Decentralized Web Summit. But in the end, what this really looks like at a high level is sort of re-architecturing the structure of web networks, right? So we're moving from something like on the left, which is a centralized network, to something like on the right, which is a decentralized network, right? So it's not a full distributed network, it's a decentralized one in which you still have local nodes hosting content and peers connecting through to that and routing through the network overall, right? So it is different than a fully distributed network. It's a decentralized network. At a deeper level, what we're really talking about here is a whole stack of peer-to-peer protocols and technologies built around sharing data or content. So whether that data is monetary transactions, cat photos, or a live streaming online course, the idea is that we all, peers and nodes on the network, host the internet and web, and we all become host and client. And we're continually using, defining, and moving the data that drives the web. So if you want, you can kind of split this whole stack up into sections, similarly to how we would talk about the current web and the way it's structured now. So we have apps, or in the case of a decentralized system, dApps, decentralized apps, that are running on top of the whole thing. And they're using data. And maybe it's some sort of a social media profile or a monetary transaction system, whatever that may be. Then we have protocols, the conventions and tools that we use to actually define the data. So what data can we transmit? How does that data need to be structured? Do we chunk it up into small bits or send a stream of information? How does this work? And then we have the core protocols and networking layers that are actually designed to then move said data about the internet. Exchange data between peers, route data from one peer to another, network connectivity, that sort of thing. So in this course, we're going to interact with the upper part of the stack throughout the course, and we're going to talk about the lower part of the stack. It's kind of the structure we're taking here. But before I do that, let's take a quick pause and see if there are any questions or issues before we move on to any further topics. So we're going to get hands-on in a little bit here. Okay, I'm checking the audience tools here. We look like we're okay here on the Slack channel. Okay, great. Okay, so if decentralizing or decentralized sharing of content is kind of our goal here, then we obviously need some kind of a system that can support this task. And that's where the interplanetary file system, sort of topic for today's lecture, if you will, comes into play. So it's obviously a very cool name for a piece of technology. And really the functionality or the sort of lofty goal that it has for itself matches this coolness of the name. So IPFS is a distributed file system that seeks to connect all computing devices with the same system of files. And that's really quite similar to the whole idea of the original web, right? A system of interconnected computers sharing files, HTML, or something like that. But it's actually more like a mashup of, say, BitTorrent, Git, and a whole slew of other technologies and protocols. And in general, the project's goal is to become a or even the new major subsystem of the internet, so potentially even replacing HTTP. So we'll see if that comes to fruition. But the idea is this thing is can be very easily explained as a peer-to-peer hypermedia protocol addressed by content and identities. And there's a lot of sort of marketing blurb around this, which you can kind of jump on. It goes something like IPFS is a protocol, a file system, a web, a software stack, a crypto system, a peer-to-peer network, a content delivery network, blah, 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 all rolled into one. And even the website says that IPFS is the decentralized web. So that's great. Decentralized web solved. And it's easy to get bogged down in sort of some of the big lofty promises of IPFS, but it is actually a fairly impressive project. And I highly recommend you watch this talk by Juan Bennett at Stanford, where he kind of does a great job of explaining the motivations and ideas around IPFS. But the point I'm trying to make here really is if IPFS is a pretty big idea, so just watch a bunch of YouTube videos and you'll understand it. Actually, no, we will break down throughout this course some of the actual underlying technologies and ideas that go into actually making this work, so that you don't have to watch a bunch of YouTube videos. And there is a lot going on, right? The IPFS project has slowly broken out into a bunch of sub-projects, each sub-project tackling a very specific piece of that protocol stack that we were talking about earlier. So you have things like file system interactions. That happens in Go IPFS, or the sort of reference implementation of IPFS in the programming language Go. You have things like self-describing identifiers that are part of the multi-formats project. You have fancy data structures that are part of the IPLD project. We'll talk about that on Thursday. And you even have distributed data structures and networking layers and cryptographic primitives as part of the libp2p project. And so these are the sort of icons at the bottom here. And the idea is that all of these sub-projects support the broader idea of IPFS as this sort of overarching P2P web system. And a big piece of that, of course, is storing data. because that's ultimately what we're sharing is data between peers. So if we take another quick look back at the stack, and this is a very simplified stack. In fact, it's really the stack as seen by IPFS project. But if we take a look at the stack, we can sort of map these components onto the stack. So as I said, this is a pretty IPFS-centric view of the decentralized web, but it gives you a good way to think about how these things work, and hopefully kind of gives you an idea of what we're going to start to cover throughout this course. So what we really have here is a modular set of functions, tools, and protocols, and even ideas that help make up this system for exchanging content between peers. So we've got IPFS, IPNS, IPLD, libp2p, and all sorts of things in between to move and interact with data on the web. Okay, so I'm going to take a step back to some higher level stuff. Then in a few moments, we'll dig into some actual interactive stuff with everybody. So a key difference that we kind of have to think about when we're talking about the difference between a decentralized web and a centralized web is actually how content is addressed and shared between peers. Okay, so right now HTTP we access content based on where it is. Okay, so what server it's sitting on. On the new decentralized web, we access content based on what it is. Okay, and this simple concept kind of flips the whole web addressing model on its head. But I think it's actually a lot more intuitive to think about. And here's an example of why. So if I ask someone for their favorite cat video, they probably aren't going to say something like, oh, haha, the one on the server at this subdomain under this file path /hilarious-cat.mp4. Right? They're not going to describe where to find the video. What they're going to do is they're going to describe the contents of the video. Oh, haha, the one where the cat knocks the glass off the counter, thug style, classic. So another example, and this one gets used quite often, is maybe finding a book in a library. Right? I'm probably not going to tell you where in the library to find a book. Oh, walk down the third hall. It's about 7 feet down on the left side. I'm probably going to give you some kind of information about the book and have you find it yourself based on the ISBN or the author name or something like that. So I'm going to use the content of the book to find it. And I'm going to use the content of the video of a cat to find it. So here's another video that explains some of these concepts that we're covering right now. So I highly recommend you watch that after this session. Okay, so how does this content addressing work? We need to come up with some way to create a fingerprint of the content and then use that fingerprint to find the content that way. So similarly to finding a book, where we'd use an ISBN number, in practice, content addressing systems such as IPFS use a cryptographic hashing functions to create fingerprints. So basically, we take the raw content, in this case, the sort of digital data that is a cat footprint, and we run that data through a hash function to produce what we might call a digest. Right? This digest is guaranteed to be cryptographically unique to the content of the file, or image, or whatever it is, and that file only. If I change that file by even 1 bit, the hash will become something completely different. So quick aside here on cryptographic hashing. A cryptographic hash function is really just a one-way algorithm that is used to map data of arbitrary size to a bit string of some fixed size. And generally, these algorithms are deterministic, so you get the same hash if you use the same content each time. They should be pretty fast to compute because we've got a lot of data to share between people in a short amount of time. They should be infeasible to reverse, except by basically just brute force trying a bunch of things until you figure it out. The hashes themselves should be uncorrelated with their content. So a small change in content could produce very different hashes. There should be no way to sort of link the content to the hash that you get from that content. And collisions, where two different outputs have the same hash, should be infeasible. Right? So it should be pretty much impossible to hash two different files and end up with the same hash. In practice, IPFS uses the SHA-256 hashing algorithm, but we'll see later on you could use just about any well-known hashing function that you want, and there are some good ones and some bad ones. And we'll talk about hashing a little bit more throughout the course. Okay, so if we jump back to our little cat example, what we've done is we've got the raw data, we've hashed it. Now what? Well, what we want is a content identifier so that we can actually identify this content. We want the fingerprint that we're talking about. So what we want to do is take that digest and convert it into something that IPFS and other systems can use to locate it. And it's this pretty non-trivial problem because we kind of need to think about what if things change in the future and we want to change the way we address a particular piece of content. What if someone invents a better hash function or a faster hash function? Even the IP system that we use to identify and locate servers on the web has undergone some upgrades from IP4 to 6 and all these things. So we need to kind of future-proof this system. And so what we end up with is something which the IPFS community or the IPFS developers call a CID, a content ID, right? And you may have seen something like this before, and they all seem to start with a QM and then a bunch of random alphanumeric values. So the QM there is actually because those hashes are actually something called a multi-hash. And this is pretty neat because the hash itself actually specifies which hash function was used to hash it. So it specifies which hash function was used and then the length of the hash output, right? So that fixed bit string. So in most of our examples, the first part is in hex 12, which denotes that this is a SHA-256 hash function. And if you go to the multi-hash GitHub page, you'll see a table which describes the codes used for various different hashing functions. So this is where the QM comes from. And then what we do is we base 58 encode the whole digest to make it a little bit more human readable. And base 52 encoding is something that came out of the Bitcoin project. It's sort of similar to base 64 encoding, except it gets rid of things like zeros and O's and capital L's and I's and a few non-alphanumeric characters so that it's a little bit more human readable and it makes for better URLs and things like that. But anyway, all of this is because we want a future-proof system that lets us use different hashing and fingerprinting mechanisms to address content. So if that new awesome hashing function does get invented, we can just change the first few bytes of a multi-hash, and now IPFS hashes no longer start with QM, but because we're using multi-hashes, those old QM ones will still work, and the new ones will work, and everybody is happy. So we have upgrades built into the network. Okay, so once we have these content identifiers, what do we do with them? Well, we can request the network, or we can request the content from the network. So instead of saying, hey, computer across the internet, I want this file, you say, hey, network, can you find me the file that looks like this? So I can make it available, say I've got a file on my computer, my cat photo. I can make it available by adding it to the IPFS network. And then when my friend wants to access that file, they can simply ask the network, who has this hash? And they'll ask the network, and someone will say, down on the right there, I know a guy. He's way across up there on the left. And then our friend requesting the data will route over to the person who has the content. The person with the content will send it back, and everybody's happy. Now, once my first friend has that file, my other friend can technically get that file now from them or me. So this means that there's no centralized point of failure. And since we're requesting the content directly, we know we're going to get what we asked for and nothing else. And I'm going to elaborate on that a little bit moving forward. So what we have is a distributed, authenticated content sharing system, right, where people can pull information from various places. to access the content that they need. So what does this all get us? Well, what it gets us is a permanent web. Content address links are permanent. The links permanently point to exactly that content. Because those hash functions are deterministic, we know that if we hash and we get a particular hash, that content describes a specific piece of content. So this is a potential solution to the problem of link rot by creating a persistent data structure. And then there are tools on top of it to enable dynamic content, and we're going to play around with that on Thursday. But the idea is we have these permanent links to content, and as long as someone has that content, the links will work. The system can be very efficient. Right? The network provides deduplication and scalability by default. Okay, so the more peers we have on the network, the greater these efficiencies, the lower the latency, and the more the content becomes rootable. And the way that works is sort of my example previously. If I have a file and I share it, then one of my colleagues accesses it, and then another colleague accesses it. Now each of them have that content. So the next person to request it can actually request it from any of us or all of us. And we actually have a process called bit swapping, which is similar to BitTorrent, where you can actually pull bits and pieces of the files from everywhere. And the more peers that are hosting a particular file, obviously, the more efficient this can be. Content addressing also increases the integrity of the data that we have on the web. If two particular hashes match, or if the hash that I get back matches to what I requested, I know I'm getting what I asked for because it's the only content that could possibly have produced that hash. So the content you download is cryptographically verified to ensure that it hasn't been tampered with. So this sort of prevents man-in-the-middle type attacks to some degree. It also enables distribution. You don't need a connection to the wider web. And in fact, you can actually store content locally and shut off your connection to the wider internet and still interact with the content that you have locally between computers. So content can actually be stored and served close to a user, possibly from a computer in the same room. And that seems very intuitive, right? Yeah, obviously, if my friend is sitting next to me, he's got a picture on his phone, I should be able to access that picture from him right there. We're in the same room. But that's not how the current web works. The current web would require him to upload that to, say, a centralized file storage system, maybe Dropbox, send me a link. I would then go and I would fetch that content from that centralized place and bring it down. And in fact, if you ask people who are sort of unfamiliar with web technologies, they would probably think that that decentralized local system is how things should work. It also lets us store data together. And what we end up doing is sharing the responsibility for data preservation on the web. If you hold a copy of data on any device, or you pay through Filecoin or something like that, which we'll talk about later in the week, you become part of the network. And even if the original publisher goes down, the content can be served by anyone. So you can circumvent things like government censorship and things like that by sharing the preservation of content online. Okay, so we're running a little bit low on time. So that's sort of like the first layer of our decentralized web IPFS onion that we're going to cover today. Hopefully, I've taught you a few things. But remember, if this was a bit slow for you, we're going to start to move faster as the sessions progress. So this is really just kind of getting everybody on the same page and pointing out links to YouTube videos that you can use to fill in gaps. If all of that was a little too high level for you, we are going to start to dig deeper as we move further. Also, don't forget to go back and watch those YouTube videos and check out the additional materials that are linked at the end of this slide deck. All right, so I'm going to take a quick look to see if there are any questions. And then in the meantime, we'll just kind of continue on. So we've got a few more concepts and technical bits that I want to cover. So for the rest of the session, we're actually going to be learning by doing, and we're specifically going to be interacting with IPFS from the command line. So take a minute, if you're following on with us live, to fire up a terminal and get ready to start copying and pasting things into that terminal. Now, if you don't want to follow along, or you don't have a terminal handy, or you want to go back and maybe do this later, that's fine too. most of the outputs will be on the screen here, and I'll actually be jumping back and forth to my terminal here as well, so you can see kind of some of these outputs live. Okay, so let's jump in. First things first, if you don't have IPFS installed already, you're going to want to do that. So the easiest way to do this so that you can actually update IPFS at a later date is to use the IPFS update command line utility. And so the easiest thing to do is you can just go and download that. You can do this all from the command line, or you can do this manually by copying and pasting that long tar gzip file or URL there using the centralized web. So you go and download that, unzip it, open that file, and then run the install.sh command there. If you prefer to download a binary and install it that way, you certainly can do that as well. That link provides a link to get there, and then you can just download the one for whatever system you're working on. Our survey revealed that most of you seem to be using either Mac or Linux, which means that the command line is probably pretty familiar to you. But either way, you can go download that, you unzip it, and you just follow the instructions that are packed in there. So if you'd like, you can run these commands, and I'm going to go ahead and run them with you right now, just so you can kind of see what that output might look like. So we're going to pop over here to a terminal, and I've just got an interactive terminal hosted on a page here so that you can kind of see what's going on. So we'll run wget, which is just webget to download that content. All right, and then we'll let that download. We'll untar that content. We'll change directories into that particular directory. And we'll just run the install script. Great. And if everything went according to plan, you should see some output that looks similar to that. Okay. Now what we can do is actually, I'll just jump back to our slideshow. Now that we've got that installed, you can actually list the versions that are available for the actual versions of IPFS that are available for download and installation by running IPFS-update versions. And then you can install whichever version you want. I recommend for our course here today that you just run IPFS update install latest, which will just go out and get the latest version of IPFS so that we know we're working with sort of cutting edge stuff here. So I highly recommend, if you can, that you go through and you do this right now. I've obviously already got it installed on my system, so I'm not going to run that again. If you have any issues installing, please feel free to hit us up on the Slack channel or post a question to our audience tools question and answer area here as well. Okay, so I'm going to assume everybody is an expert at all this and that everything is installing nicely. So we'll move on. So once we have IPFS installed, we need to initialize our repository. And we're going to do that just using a single command called IPFS init. And what that will do is, by default, it creates our local global repository at your user directory in a hidden folder called IPFS or .ipfs. When it does that, it also generates public and private encryption keys and an associated peer ID. And we're going to talk more about that on Thursday. So we're going to go ahead and use the default repository configuration. And if you run IPFS init, you should get some output that looks a little bit like mine here. IPFS init. It'll generate that key pair, it gives you your peer identity, and then it says, to get started, you can enter IPFS cat, that file. So that's just a part of the sort of default documentation that comes with IPFS when you install it. And so if you run that, you'll see something printed out to your screen. Okay. So once you've got that repository initialized, we can start to connect to the distributed web. And in order to do that, what we'll do is we'll start our local daemon. I have no idea if I pronounced that word correctly, but let's hope I do. And we'll automatically connect to a bunch of bootstrap peers. So these bootstrap peers are configured peers that are already running out on the IPFS network that already have connections to various peers across the network. And when you fire up your peer, it will go out and it will connect to those bootstrap peers. And it basically bootstraps your peer so that it knows where various peers are across the network. It allows it to right away build up a distributed hash table, which we'll talk about in a moment, and start to do things like routing for content. So you can run your IPFS daemon. I recommend opening one terminal and running that, and then opening up another one to then start interacting with IPFS. You can also run that with a trailing ampersand symbol, and that will give you control back, but it's easier if you just open a terminal, run IPFS daemon, and let it sit and run. And you should get some output that looks something like this. When you initialize that daemon, you should say things like this, and it'll print out what ports you're listening on for the IPFS swarm, where your server is listening, and your gateway. And then it should say something like your daemon is ready. If your actual port values are not the same as this, that's all right. Probably yours will default to API server listening on 5001 and gateway listening on 8080. Okay. So if you want, you can go ahead and run IPFS swarm peers on your terminal. And what you should see, here we go, IPFS swarm peers, is a list of multi-addresses, or addresses where all of the peers that you're connected to are sitting. And we've got a bunch of peers here on my IPFS node. You may have fewer or more, it doesn't really matter. But that gives you an idea that we're actually connected to the decentralized web. Now, for those of you who prefer to interact a little bit with a user interface, you can actually fire up localhost :5001/webui and actually interact with this through your browser, your default browser. And you'll get information like what your peer ID is, where you're located, connections. You can actually get a neat map of the peers that you're connected to, different files that you're pinning and sharing and things like that. So if you prefer that sort of thing, I recommend playing around with that. But let's actually get going and do some things here before we run out of time for today's session. So we'll start by catting a photo of a cat. So IPFS cat, and then you give it a long address to a particular file, and that address is the content address for that particular file. And you can save it to your local hard drive, and then open it, and you'll get something that looks a little bit like this, right? And if we, we jump back over to our command line here, and I run this command, open cat TV, I get a nice picture of a cat that opens up on my screen. And it looks something like this. All right. So pretty simple way to start, and this is a classic example that you see on a lot of the tutorials and things for IPFS. What we've just done is queried the network for that particular IPFS hash and downloaded it using our own IPFS peer and opened up that content. And now we can start to play around with other things like adding content to the IPFS network. And you can go ahead and run through this example here if you'd like, where you can just copy and paste these this example here. I'm not going to necessarily run through this with you, but if you go and run this, what you're going to end up doing is basically adding the text I heart IPFS dash and your username to the IPFS network. And then you're going to access that content over the IPFS over an IPFS public gateway. So that's the link there, https://ipfs.io/IPFS, and then the hash that you just generated. And it's a pretty simple thing, and you'll just see a web page with a little bit of text, nothing particularly fancy. But what has just happened is that you have added content from your local system to the IPFS network. That gateway has gone and you've served a file from your computer. The gateway queried the network, potentially found your machine, requested the file. Your machine sent that file to the gateway, or that content rather, and then the gateway sent it back to your browser. Right? Now we know that it's probably finding your system or your peer because we specifically added that who am I or your username to it. Now, if you just added IPFS, chances are someone has already added content that looks like that, and you might have fetched it just from them. But by actually adding your own username, potentially you're creating a unique new value with a unique new content ID, and you will go out and access that from your system. And this brings us to our next aside, which is distributed hash tables. So when I say things like query the network or ask the network or get it from the network, what I'm actually saying is query the distributed hash table. Okay, so what does that mean? First, a hash table is a data structure that stores information as key value pairs. So think of something like a Python dictionary or a JavaScript object or a document-based database of some kind. Similarly, a distributed hash table, or DHT, is a hash table where the data is spread across a network of nodes or peers. And all these peers are all connected or coordinated to enable efficient access and lookup between those nodes. Obviously, in a decentralized system, we need something like this to help peers discover each other and content. So a DHT is nice because we have a decentralized, fault-tolerant, and scalable data structure that we can query for content addresses. So our peers don't require any centralized coordination because each peer really only knows about a smallish part of the network. And through smart redundancy, the system functions even when a particular node fails or leaves the network. So we've got a little bit of redundancy so that if I leave, the information that I had about the hashes doesn't leave with me. And then finally, because no peer knows everything, the system scales really nicely. We can accommodate millions of peers. And this is a pretty common technology in most peer-to-peer systems. So IPFS uses a distributed hash table for peer and content delivery. And it looks, something like this, where we've got this ephemeral distributed network cloud with various peers that are connecting and disconnecting. And each peer knows some information about the data and its content ID. And when you bootstrap connect to various peers, you can start to say, hey, peer, do you know where this thing is? And we can start to find out where it is by querying the distributed hash table. In IPFS, the keys that we use are the CIDs, or the hash over the content. So if I ask the DHT for a particular CID, my peer will look it up in the distributed hash table and find out which peers have that content. In practice, IPFS uses something called a Kademlia-based DHT, probably mispronouncing that. This is pretty common in peer-to-peer networks. The idea is it essentially uses the ID of peers to get incrementally closer to the peer with the desired hash. And each step finds peers closer to the key until the contacted peer returns the value that we're looking for, or we can't get any closer to it. You can think of this sort of like a reasonably efficient, log n search. All right, so we search through log n peers during our search of a total of n peers in the system. Those are pretty standard in terms of efficiency search algorithm. So normally, when we access and share content on IPFS, we'd use the high-level add, get, and cat tools. But we can also query the DHT directly if we want. So what we can do is we can find peers that actually can provide a particular bit of content. And if you run IPFS DHT find provs or find providers in your terminal, you'll probably get something like this. And this lists out a maximum of 20, I think that's the default, peers that are currently hosting that content. That happens to be a picture of a cat, I believe. And if we want, we could pick one of those particular peers, and we could say, oh, okay, well, give me the address of that particular peer. And that's where this next line, IPFS DHT find peer. And we can query that, and it should eventually return back the multi-address or the address on the web of that particular peer. It may take a little bit of time to find that, but you can run that yourself and see the output. And we're actually going to cover that a little bit more in subsequent sessions, including the idea of a multi-address. Okay, so we're almost out of time. There's just a few additional things that I'd like for you to play around with between now and our next session on Thursday. So what you can do to make sure you kind of understand how content addressing works is follow through this example where you create an empty directory on your desktop or wherever you want, add a new file with some content, and start interacting with that content. So you can first create some content version 1 of my particular text file, and you can make sure that you can get that content back. You can add it to IPFS. You can access it via IPFS. And then what you can do is you can then, instead of sending the file through IPFS, your my textile file or my text file, you can actually just send the content or add the content directly to IPFS in that next line, version 1 of my text. And what you should see is that the hashes you get back are identical. And they're identical every time you run this. What that's showing you is that IPFS is addressing the content, not the actual file itself. Right? So that my text file .txt could be named anything, it could be anywhere, but what we're really addressing is the content of that file, not necessarily the file itself. And then related to your homework, you're going to want to make sure that things stick around. So normally when you're interacting with IPFS on the command line, it will cache the files that you interact with. So if you cat a particular file, it's going to cache it locally so that you can access it later. And the idea being that this makes things feel like everything is local to your system. But as time goes on and you interact with more files, eventually, if you're not using it, will probably get garbage cleaned up. So objects that aren't in use will get cleaned up, unless you tell it to pin that object. And pinning the object basically says, don't garbage clean this up. I want to keep this around. Right? You can even pin things that you don't currently have locally, and what we'll do is bring it in and pin it locally. What this allows you to do is things like host particular files. So if you had a blog that you wanted to host on the decentralized web, you could create that content, add it to IPFS, pin it on your server, and have that running there, and have it and know that it's always going to be available. this concept of pinning is going to come into play big time when Filecoin comes online. Again, we'll talk about that later in the course, where you can actually pay people to keep things around for you, or pay the system to keep things around for you. Okay, so that's it for today. We've finished just about right on time. So before we get on to our next session on Thursday, make sure that you've downloaded and installed a recent Node.js version. If you're on a Mac, you can just brew install node. If you're on Linux, you can sudo apt-get install node. If you're on Windows, it's probably easiest to just download the binary directly, unless you're on Windows 10 or something like that, in which case you can use your developer console and do as the Linux does. You'll also want to probably fork and clone our template repository that we have up on GitHub. So you want to git clone that DApp template on the Textile.io GitHub page. And then just make sure that you can quickly build the basic product or project. And actually, I'm going to fix that text because this should match this. So you're going to git clone that, change directories into that project, and just make sure that you can install and build the project. You don't need to do anything more than that before next week. And in fact, we'll run through this quickly again next week. Okay, so just some homework, and then I'll leave you to go about your day. Try to have this done before next session, which is on Thursday. So your homework is to go out, find your favorite XKCD comic from the IPFS-based archive, and the links don't seem to be coming through on the slides. So I will post that I'll post the link in the comments, and I'll update the slides after this. But you can also just go to xkcd.com, pick a comic, download the file for that comic, download the image for that comic, and then pin it to your local IPFS peer. While you're at it, create a small text file that describes why that comic is your favorite comic, or whatever content you want in there. Obviously, keep it clean. And then add the two files to IPFS, wrapping them in a folder. Now, this is going to require a little bit of Googling on your part to figure out how to do that. But it should be a pretty quick little and fun example. Then what you can do is, we'll keep it pretty basic, send me an email with your resulting hash prefaced with IPFS/ for evaluation, if you want me to evaluate it. That's pretty simple. So if you want a bigger challenge, you could do the same, but you could notify me via PubSub. And we haven't even come close to touching this topic, so it'll require a little bit of research on your part if you want to do that. You might also want to email me just to make sure that it worked. And then if you want to get even more tricky, you could use IPNS to publish your comic and text folder and send me your peer ID. And so in that case, you might want to preface it with IPNS rather than IPFS, just so I know what you've done. We are going to cover IPNS stuff on Thursday, so feel free to not do that, and we'll cover an actual practical example of using IPNS on Thursday. Okay, so those should be some kind of fun examples. Here's a slide with some additional resources that you can kind of play around with. As I said, there are a lot of videos out there covering sort of broader topics that we skipped over today and will mostly leave throughout this course. I'll continue to post videos throughout the slides that give you a better idea of what's going on. But in general, there's a lot of useful material out there. And really, our goal with this course is to provide a resource for you to help you find those things and to help make sense of some of those things. A lot of the material that we're covering in this tutorial series is actually available, similarly on the Textile blog. So that's medium.com/textile.io. We've got a bunch of tutorials, examples, and announcements about what Textile is up to. So far, we've talked mostly about IPFS. We will mention some other projects in the sort of decentralized web storage space. things like ZeroNet, MadeSafe, the DAT project, Freenet, Blockstack, a little bit of Ethereum. We will talk about these things throughout the week, just to give you a kind of flavor for what this space looks like. Again, we'll be providing videos, links to some of the blogs for these projects, things like that. But if you have any questions or you would like to dig deeper into a particular topic, don't hesitate to post into our Slack channel or post to our Q&A question slides here at the top of the screen. And we'd be happy to interact with you that way. And with that, I'm going to sign off. And we'll see you on Thursday.